Couple more k-mapping examples. First, use k-mapping to produce minimum sum of products and product of sums expressions for a circuit that takes a BCD nibble and determines whether it's divisible by 3 or 2, but not both. Implement the expression using only NAND gates. Okay, so a bunch of stuff to unpack here. So the circuit needs to take a BCD nibble, so binary coded decimal for 4 bits, and then determine whether it's divisible by 3 or 2, but not both. So here we go. Let's insert a table. First, let's get the binary counting going here. And let's call them ASDF. Okay, and we're going to go 0, 0, 0, 1. Whoops, let's start with 0 actually. 0, 0, 0, 0, then 0, 1. And then we'll go 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Okay, so that's 8 cells. And now we'll go and add 8 more to make the numbers between 8 and 15. So this is the full set of inputs that we can have with a nibble, so half of a byte. Now what we're going to do is come up with the truth table for what the output would be here, y, and y is going to determine whether the input number was divisible by 3 or 2, but not both. So 0 is divisible by both. So this is going to be a 0. 1 is not divisible by either. 2 is divisible by 2. 3 is divisible by 3. 4 is divisible by 2. 5 is not divisible by either. 6 is divisible by both. 7 is divisible by neither. 8 is divisible by 2. And 9 is divisible by 3. Then beyond this, 10, 11, 12, 13, 14, 15, these numbers are not valid binary coded decimal. So those are going to be don't care conditions in our truth table. Okay, next step is to convert this into a k-map. So let's insert another table. And this one's going to be a 5 by 5. So what we'll do is we'll list AS along the left and DF along the top. 0, 0, 0, 1, 1, 1, and 1, 0, counting in gray code now. Now, let's go through the truth table. So for all zeros, it's divisible by both. For 1, divisible by neither. 3 is divisible by 1. 2 is divisible by 2. So you could sort of go through and think through the numbers and just come up with the logic once again, or you can look at the truth table above to come up with it. In this case, where we can jump right to the expression, you could argue that we don't really need the truth table, and we are good to just come up with things directly. So 6, this is 7 divisible by neither, 6 divisible by both. Then we've got 8 divisible by 2, and, oh, that's not 8. That would be 1, 1, 0, 0, which is 12. So that's a don't care condition. Don't care, don't care, don't care. And these ones are also don't care. This would be 8, which is divisible by just 2, and that's divisible by just 3. Okay, so here we go. Let's double check. We've got a total of 1, 2, 3, 4, 5 zeros, and 1, 2, 3, 4, 5 ones. All right, so it looks like everything worked out the same as it did earlier. Now let's think. From a zeros perspective, we would have this these two grouped as 1, and then we can, and that's the best we can do to catch this one in there, because you can't go left, you can't go up, you can only go right, and that's as far as you can go to the right. Now this one we can catch with a block of 4, and same thing with this one, you can catch that one also with a block of 4. So the product of sums expression, maybe we'll get this hooked up in, let's draw the circles for this out directly. Okay, so we'll take a screenshot of that. We'll go over to our paint.net. We'll select the rectangle, double click to have a filled in one, and then we'll maybe get some red that has some partial opacity in order to draw this out. So now that we're over here, why don't we do the sum of products term first? So we'll have one box right there, looks like. In order to get this one, we've got to use that box. That's the best we can do for that one. And then we can get these two. Oh, this one's pretty nice. We can get those two with this box. Okay, so we got one box of size 2, one box of size 4, and one box of size 8. Okay, so this is the SOP implementation. And here's what we got for that. So let's see, the box of 2 has S in common, and it has D bar, F bar. Now we're going to add to that the box of 4, which has S bar in common, and also D in common. And then add to that this box of 2, the box of 8 here, which has A in common, and that's it. So we've got A plus S bar D plus S D bar F. Now we can go and double check with our truth table whether or not this logic actually works. So this says, okay, let's just pick numbers at random. If we have all zeros, we should get 0. And yeah, all of these require at least one thing to be true for it to give true overall. If only F is true, we should get a 0. Yep. So specifically, you can't get anything being true unless you have either S, D, or A being true. So let's look across. All of the trues have at least one in those entries. And everything where A is true is giving us a true overall. Okay, yeah, that's valid. Now, what about D is true and S is not? That's sufficient for us to get a true. So that's these ones there. That's right. And then those ones over there. Okay, so a few cases that we've tested makes it look like we haven't made any mistakes with the logic. That wasn't exhaustive, but that's okay for a quick check. Now down to the product of sums expression. So we'll undo those rectangles, and we'll now draw in rectangles for our zeros. Okay, we got one there. We're going to need one there, and now we can use one over here. Okay, so I think that's as good as we can get. So let's see what we end up with. So the box of 2, you think about what's in common among all of the entries. So everything is 0 except for F, and F is not in common among those. So we'll say A or S or D. If all 3 of those are 0, then we have a 0, and that's what this box is representing. Okay, now this box over here, we have S is a S is a 1, so if we put an S bar there, and then for F is also a 1, F bar. So the way this logic works is you say if A and S and D are all 0, that's the only situation that would make this thing 0, and we're going to get a 0 overall if that's true, because we're multiplying this by the other terms. Now this one, if S and F are both a 1, then we get a 0 as well, and that's what this box represents. So that's how this term comes to play. Same idea for the last box. We're going to get D bar along the top, and also S bar along this side here. Okay, so there we go. There is our minimum product of sums expression. So now, returning back to the question, use K-mapping to produce minimum SOP and POS expressions for a circuit that does this, this logic that we were writing out. So that's good. And then we need to implement the expression using only NAND gates. So we can pick either one. of these expressions and implement it with a NAND gate. So let's demonstrate how we could do that. There's more than one way to do this. So let's take this expression first and try to convert everything into NAND gates. So a NOT gate, you can use a NAND gate to do that just by wiring both of the inputs into that into that same gate. We don't have any ORs, so we're going to have to clear that out. And an AND you could complete by taking a NAND and then inverting it. So that's how we're going to be doing ANDs. Now for this part, we've got an AND and then another AND, and both of these things are so we could sort of use two AND gates for that, and we could use an AND gate for this, and wherever we have an AND gate, we could just use two NAND gates. Let's try to factor this and see if we can get anything better. So this thing can be factored into, let's see here. There we go. So the OR is kind of like a NAND of each of the inverse of each of these things. So just using De Morgan's law backwards. Now this AND has turned into a NAND, and that's better anyway. Okay, next thing we're going to do is get rid of the next OR by factoring this out. And now we've gotten rid of that over bar for the second term. Yeah, so just double check that we did it right. We replaced the OR with a NAND on this stuff. And so replaced the OR with an overall NAND, and the two inputs are inverted. Okay, so this one did have an overbar, and now it doesn't. All right, so let's see. We've got one NAND for that whole thing. We've got another NAND over here between this and an AND of D bar and F bar. And over here, we've got a NAND of those two, and then we're ANDing that with A bar. So let's see. So if we wanted to count up the gates that we needed for this, we need one NAND overall, and then another one for this, and then we need an AND, which counts as two more, and two inverses, which is another two. So that was 1, 2, 3, 4, 5, 6. Then over here, 7, 8 to AND those two. 9 for this NAND. 10 and 11. Looks like 11 NAND gates total to get that thing to work. Okay, so the next thing that we can do is try to convert this to NAND logic. So I think let's write down 11 NAND gates. Down here, the way we'll do that is factor these ORs into a NAND of S and D after inverting both of them. And then this one can be converted similarly into a NAND of S and F. And over here, we've got a 3-input OR. So let's convert that into a NAND of S bar and D bar. And we'll say that that's the same as over here. NANDing those guys and that. Okay, great. So now let's see what we need. We need 1, 2, 3, 4 for those inverses, 5 for that, and that's 6, 7, 8 for that NAND, and then we need to AND this together. That's 9, 10, and then AND that 11, 12. So it looks like 12 NAND gates. if we counted that right. So sort of similar, no big advantages to doing one version rather than the other if you have only NAND gates to use. All right, so next problem. Use K-mapping to produce minimum sum of products and product of sums expansions for a circuit that takes a BCD nibble and determines whether it's prime. So we're going to take a BCD nibble. This is similar to what we did in the sample lab, except now the input is BCD. So we can actually copy a lot of the stuff that we just used and reuse some of these tables rather than having to write out ASDF again. Okay, so what we're going to do is determine whether the number is prime. And for this, let's take that 0 and 1 are not prime. I think that's how they're usually defined. Then 2, 3 is prime, 4 is not, 5 is prime, 6 is not, 7 is prime, 8 is not, and 9 is not, and the numbers above that are not BCD. Okay, so then up here, we've got 0, 0, 1, 1 for 2 and 3. 4 is not prime, 5 is. 6, this is 7. 7 is prime, 6 is not. And 8 and 9 are not prime. Okay, so let's check that this works. We have 4 ones, 4 prime numbers, which would be 3, 2, 5, and 7. And everything else is not prime up to that limit for the BCD numbers. Okay, so first thing, sum of products expansion. So we'll take a screen clipping of that and we'll put that over to Paint here. Sum of products, we're going to collect all the ones together. So the biggest rectangle that includes this one would be that one. Ooh, then we can actually just get the other two with a rectangle that wraps around like that. So we only needed 2 to do this one. That's all right. Okay, and this expansion would be, let's see, we've got S true, and we've got F true. And then the other term would be D true and S false. Okay, yeah, so there is our sum of products expansion. And now let's collect the whole thing under a single NAND of that and NAND of that. Okay, so this we needed one NAND gate overall, and we needed a NAND gate there, and we needed a NAND gate there, and we needed another one to invert the S. So that's only 4 NAND gates. Okay, let's try the product of sums expansion. Whoops, so we'll undo those. And now, let's see, what could we do? What's a tricky 0 to catch? This one. I think the best way to catch this 0 is to go around like this. Yeah, around the side. Then what? Ah, well, we only need one more rectangle for this one as well, and it's that one. And that's generally the strategy that I think is the best to employ, is look at the trickiest one to catch and then try to do that one first. Okay, so product of sums expansion for this. This we've got in common that S is a 0 and D is a 0. So that gets inverted into this term. And then you think, okay, if S is 0 and D is 0, then we're going to get 0 overall. Now for this one, we've got in common that S is a 1. So there's our S bar. And then we've got that what's the other term? F is a 0. So, or F there. All right. So now let's implement that with NAND gates. So I think what we want to do here is invert the whole thing at first. No, because then that's going to turn into an OR. Okay. So what we could do, we're ANDing this. So let's work inside that those ANDs, and we'll convert this into a NAND of S bar and D bar, and same thing here. A NAND of S and F bar. Yeah. And then we just NAND, we AND that overall expression. So this is, this one's definitely not as good as the previous expression. This requires 2 NANDs just to implement that AND overall. It requires another one for each of those NANDs, so that's 4, and then 5, 6, 7 for the 3 inverses, which would be 7 NAND gates. All right, so what we did is we took 2 examples of logic expressions. We started off with the truth table and then made Carnot maps and implemented them with both sum of products and product of sums, and then we converted those expressions into NAND-only implementations. And actually, as I'm scrolling around here, I noticed that this question actually was to do NOR gates rather than NAND gates. All right, let's do that. So how would you do this whole thing with only NOR gates? Well, we've got an OR overall. So what we'll do is we'll convert the interior parts, sort of the opposite of what we just did for each expression. Like that. Okay, so this one requires, let's see, well, 1 NOR gate to invert each of those interior terms, a NOR gate there, a NOR gate there, and then 2 to act as an OR gate, which would be 7 NOR gates. So you might be thinking or noticing right now that by symmetry, probably what's going to happen is this version is going to be doable with only 4 NOR gates. So let's see, if we were to NOR this whole thing, then we'll end up with that and that. And indeed, we've got 1 NOR overall, we've got 2 NORs inside it, and then 1 is inverted. So that's 4 NOR gates. Great. Thanks for watching.